Okay, so theorem. This is the miracle of the day. So pay attention. Theorem. Okay, so it's a theorem that's going to analyze the out-of-sample error for the nearest neighbor algorithm because we cannot rely on the VC analysis. So the theorem is that E out for the nearest neighbor algorithm is at most twice E out star. Now I'm going to tell you what E out star is. Okay. Now there are some conditions here, with high probability as for sufficiently large n. So sufficiently large n. Okay, and it'll be clear when we prove this theorem because it's such a miracle. What is this with high probability and what is this sufficiently large n? Okay, but this theorem is really a miracle because what is it saying? It's saying that as long as n is large enough, and we know that no matter how large n is, E n is 0. Okay, what it's saying is that no matter how large, despite the fact that the in-sample error is 0, the out-of-sample error will be small. Okay, so E out is small. Okay, and that's sufficient for learning, right? So in the two-step process, we got learning by setting E in small and then getting E out to be close to E in, and therefore we conclude that E out is small. So here we are going to directly show that the out-of-sample error is small. How small? At most twice the optimal out-of-sample error. So let that sink in. At most twice the optimal out-of-sample error. Wow! What do you mean by optimal? The best that Malik can do? No. The best that an alien can do? Nope. The best possible out-of-sample error for this problem, whatever your problem is. In other words, basically the out-of-sample error that is incurred by the target function itself, the optimal way to classify. Okay. So if you could classify optimally every test point, you will get an out-of-sample error E out star. And this guy is at most twice that. So if the best you can do in your problem is 1%, and you may not know what that best is, but if the best is 1%, then this guy's out-of-sample error, okay, is approaching at most 2%. Why do I say approaching? Because, n must be sufficiently large. Okay, so that's a miracle. Sometimes people say that, the nearest neighbor, which is what this algorithm is based on, the nearest neighbor contains, roughly speaking, half the classification power of the entire data set. Why do we say that? Because, if you use the whole data set and this and that, you might be able to get down to E out star. So you can improve by a factor of, 2. So basically half the classification power of all the data is in the nearest neighbor. That's how powerful the nearest neighbor is. Okay. And we're going to now, show this theorem. We're going to prove it. Okay. And then, it'll become clear. We're going to brush under the rug some of the measure theoretic and so on, very technical details, but you'll get the basic idea for the proof. Okay, so proof. So this is really a miracle. This is a learning algorithm for which we can get a link to E out star directly and prove that it's near optimal. Okay, so proof. Now, okay, we're going to go into this general setting where the target function is probabilistic. So let f of x equals, we'll rename it pi of x just because that's the more sort of customary notation. So pi of x, we'll rename it to pi of x, which is the probability that the target function y equals +1 given x. So we're in the probabilistic setting, the more general setting. So there's a probability, pi of x, the probability P for probability. There's a probability pi of x of observing +1 given any x. Okay, that's sitting there in some sense. And if we wanted to build the optimal classifier, okay, so the optimal classifier is what? Is to say +1 if pi of x is greater or equal to 1/2, and -1 if pi of x is less than 1/2. So let's see, why is that optimal? Because, if pi of x is greater or equal to 1/2, okay, then that means the chances of +1 are larger than 1/2. So the majority of the time, the classification for x will be +1. Okay, and if you say +1, you're going to agree, you're going to get an error of 0 the majority of the time. If you were to classify as -1, you would have a higher probability of error. Your probability of error in the case where, pi of x is positive, okay, would be 1 minus pi of x, where pi of x is bigger than a half. Okay, and similarly, if pi of x is less than a half, that means that minus 1 is more likely, and so you get the minimum probability of error by actually classifying that point as minus 1. Okay, so this is the optimal classifier. Okay, let's see what's the out-of-sample error of this optimal classifier, and I'll call it E out star of x. E out star of x. Okay, because it's for x. E out star of x is going to be equal to, if it's going to be equal to 1 minus pi of x, if pi of x is bigger equal to a half, because if pi of x is bigger equal to a half, then your classifier says plus 1, and it's making an error when the true value, when the observed y value is minus 1, which occurs with probability 1 minus pi of x. So that's the probability of error if pi of x is greater than or equal to a half, and it's going to have a probability of error which is pi of x if pi of x is less than a half. And why is that? Because if pi of x is less than a half, you say minus 1, and with probability pi of x, it's going to be plus 1. So your probability of error is pi of x. Okay, and you can see that in either case, the probability of error, E out star of x, is equal to the minimum of these two. Okay, because if pi of x is greater than or equal to a half, then this guy is smaller than that guy. If pi of x is less than a half, then this guy is smaller than that guy. So we can capture both of these equations by saying that your out-of-sample error, is the minimum of pi of x and 1 minus pi of x. Okay, let us call this eta of x. Okay, so that's the best you can do, and that's what's interesting about formulating the problem this way. We can actually get an expression for the optimal error, the error made by the optimal classifier. Now we don't know what it is. That's the problem. We don't know what it is, but we do know we have an expression for the optimal error, and that's one of the hurdles with analyzing the optimal error. Okay, or with analyzing the out-of-sample error of a typical algorithm, and we don't know how you perform out-of-sample, but optimal, we have an expression for it. And if we knew pi of x, we could compute it, but we don't know pi of x. Okay. So, what we're going to do is now, and by the way, E out star is just equal to the integral dx p of x E out star of x. It's the average, the expected value of the probability of error. Okay, so you can just average over x, but that's not going to be so important. We know we can do that. Okay, good. Okay, I'll just leave it there. All right. Now, let's look at well, let's make some assumptions. We don't know pi of x, but we need some properties of pi of x. Okay, and I'll state the properties now, and we'll see why we needed them when we go through the derivation. Okay, so we'll state the properties. Property 1. Pi of x is continuous. Okay, so pi of x. This function pi of x is continuous. The optimal classifier is not continuous because it can be plus 1 when pi of x is greater than or equal to a half, and then when pi of x drops below a half, it suddenly drops to minus 1. So the classifier is not continuous, but the underlying probability of y equals plus 1 given x, that's a continuous function. Okay, and that's reasonable. Continuity is not a huge assumption for machine learning problems. Okay, and we could make more assumptions. It has bounded derivatives and so on and so forth. If you make more assumptions, you get stronger results. Okay, one more thing that we're going to need. Now, this is true for almost any probability distribution that you care to come up with. Okay, and what is that? What that is that if you take any x, okay, so take any x for all x as n goes to infinity. Okay, so as you generate a data set whose size is becoming larger and larger, okay, the nearest neighbor to x must be approaching x. So your data point, your nearest neighbor to x, so which we call x1, it must approach x. Okay. Now this is kind of obvious, if you fix x, but what we're saying is that this must simultaneously occur for all x. Okay, so there's something to be proved here, but you can sit down and prove this technical result. If you want, you can assume that the P of X is continuous and your X space is compact, and so everything is nice and well behaved. What this means is that if you're in some space, so if you're somewhere and you consider any X, okay, so you can just consider any X. Now, as you generate more and more data, your data is randomly distributed, and as you generate more and more data, look at what's happening to the nearest neighbor. It's getting closer and closer to X. Okay, that's basically what this is saying. Some kind of a regularity condition on your input distribution. And I'm putting all these assumptions inside the proof rather than, stating them as, assumptions in the theorem just to avoid clutter. Okay, so technically, I should put these assumptions in the theorem and say that, providing that pi of X is continuous and this condition holds for your probability distribution, then the out-of-sample error is less equal to twice the optimal. Okay, but I'm just trying to give you the idea behind why this result holds. Okay, so now let's look at the test error, the out-of-sample error of the nearest neighbor algorithm. The out-of-sample error of nearest neighbor. Okay, so what is its out-of-sample error at a particular test point X? So E out star for a test point X. Okay, E out. The probability of error. So the probability of error, let's call it probability of error. Okay, at X. Okay, now we're going to break it down into two cases. Okay, so what is the classification for X? The classification for X is Y1, where X1 is the nearest neighbor to X in the data set. Okay, so the probability of error is equal to the probability that Y1 is not equal to Y. Okay, and so let's analyze this. So there are two cases. Well, when you generated the X point, okay, so there are two cases. The cases are, this is equal to the probability that, Y1 equals plus 1 and Y equals minus 1, okay, plus the probability that Y1 equals minus 1 and Y equals plus 1. Okay, so that's just the law of total probability, and this is equal to the probability that Y1 equals plus 1, okay, which is pi of X1, right? Because pi of X in general is the probability that Y is equal to plus 1. If I evaluate this at X1, I get the probability that Y1 equals plus 1, and because the data points are independent, this guy is minus 1 with probability 1 minus pi of the test point X, okay, plus the probability that Y1 equals minus 1, so that's 1 minus pi of X1 times the probability that Y equals plus 1, which is pi of X, the test point. Okay, so this is the probability that my nearest neighbor algorithm makes an error on X. It's composed of two parts. The chances that your nearest neighbor is saying plus 1, but the actual Y value is minus 1, plus the chances that your nearest neighbor is saying minus 1 and the actual value is plus 1. And we just computed those probabilities. Okay. Now comes the first assumption. The first assumption is, okay, that as you have enough data for sufficiently large n, X1 approaches X for all X. So X1 approaches X. It means that as you generate more and more data, the nearest neighbor to X is just basically approaching X. So this guy, okay, so X1 is approaching X. Okay. And now comes the second assumption, that the definition of continuity, so pi of X is continuous. It means that if X1 approaches X, okay, and pi is a continuous function, so a function is continuous if and only if for any sequence that converges, the value of the function converges to the value of the limit point. So this is pi of x is continuous, means that pi of x1 converges to pi of x. So this is using my two assumptions. What are my two assumptions? x1 converges to x. Okay, that's the regularity condition. And I'm using the assumption that pi is continuous. So if x1 converges to x, then pi of x1 converges to pi of x. Okay, so that means that for sufficiently large n, this thing converges to pi of x, 1 minus pi of x, okay, plus 1 minus pi of x times pi of x, which equals twice pi of x, 1 minus pi of x. And now I'm going to come back and remind you what was the optimal error. The optimal error was the minimum of pi and 1 minus pi. Okay? So the optimal error is one of these terms. Okay? And both of these terms appear here. Okay? So one of those terms is eta of x, and the other term is less equal to 1. So if this is eta of x, this is less equal to 1. If this is eta of x, this is less equal to 1. So this guy is less equal to twice eta of x, which is equal to twice E out star of x. End of proof. That's the proof. The probability of error for the nearest neighbor algorithm on the test point x for sufficiently large data points, sufficiently large because we're applying this convergence criterion. Now, of course, you can do all the sophisticated epsilon delta analysis. If you want, you can put a bound on the derivative of p of x and get more and more sophisticated results. But the high level result is, okay, sufficiently large n because we're using a convergence criterion, a convergence result, that this guy converges to that. Okay, and when does this guy converge to that? It converges to that, providing that pi of x is continuous, and the nearest neighbor to any point x, to any test point x, converges to the test point as you get more and more data. Okay? And I illustrated that with that picture. Okay, so the probability of error is at most twice the optimal error. That's the end of the proof. Miracle. Okay. The nearest neighbor can never be worse than twice the optimal error. Nobody can do better than 2 times the nearest neighbor performance. Nobody. Not even the target function, not even knowing the target function can do better than 2 times the nearest neighbor. Okay. Now, if E out star is getting closer and closer to 1/2, then actually the theorem is becoming looser and looser because eta star is getting closer and closer to 1/2. So then let's say eta is pi, then 1 minus of eta star is getting also closer and closer to 1/2, and that 1/2 cancels this 2, and you actually the factor of 2 becomes even much smaller. Okay. So then it starts becoming closer and closer to E out star. So this bound really is becoming saturated when the optimal performance is good. Okay, that's when you get this factor of 2. Okay. When the optimal performance is bad, you actually get a factor of 1. So it's even better than that theorem says. Okay. Miracle. Look at that. Okay. The nearest neighbor algorithm is at most a factor of 2 from optimal. That's a miracle. Okay. So let's erase and come back and discuss all kinds of things, including look at all kinds of pictures. Okay, so let's sit back and take stock of what we have just proved. So the out-of-sample error for the nearest neighbor algorithm is at most twice optimal. Okay, now how does that compare with the VC analysis? The VC analysis says, E in is close to E out, and then you look at E in and decide whether or not you succeeded. With the nearest neighbor, we will not know whether or not we succeeded because E in is always 0. So we don't know E out, but we know it's small compared to the optimal. So if the optimal is large, well, then, in some sense, you failed because you're going to have a large out-of-sample error, but in some sense, you succeeded. You did the best possible. It's just that you may not want to deploy that system because the problem is just too hard. On the other hand, if the optimal classifier has a small out-of-sample error, you're within optimal. So the plus of the nearest neighbor result is that you know you're not far from optimal, and if optimal is good, then you must be good. The minus is you won't know what E out is. So you can't look at an in-sample error and decide whether or not you succeeded. We'll address that shortly. Okay. Now, let's try to get a little bit of the intuition of why the nearest neighbor algorithm is guaranteed to perform well, given that it looks like it's overfitting the data. It's always getting in-sample error 0. So let's look at some simple cases. Okay, so here are 2 data points. We have 2 data points. The nearest neighbor classifier is the line that bisects those 2 data points. Okay, so it's just the simple linear classifier with 2 data points. Let's see what happens when you get 3 data points. Okay, 3 data points. Now you see it's more than a line. It's gotten a little bit more complicated. And let's see what happens if you have 4, 5, 6, and so on data points. 4, 5, 6. You see, as you get more and more data points, the classifier gets more and more complex. Now let's think back to regularization. Okay, regularization guides the learning towards simpler hypotheses to prevent you from fitting noise. Okay? And you need more regularization when you have less data. Okay? And a similar thing is going on here. When you have a small number of data points, the nearest neighbor boundary is simple. It's as simple as it can be. It's just a line. It's only when you have more data points that the nearest neighbor boundary becomes more complex. Okay, it becomes less regularized in some sense. So you can, and some people say that somehow the nearest neighbor algorithm is self-regularizing. It only allows more complexity as you get more and more data. So it's kind of, and as you have fewer and fewer data points, the converse is as you have fewer and fewer data points, it's using a simpler and simpler boundary. And so that's basically what regularization does. So in some sense, nearest neighbor self-regularizes, and that's how we can get good out-of-sample error. We won't know what the out-of-sample error is, but we know it's good, at most a factor of 2 from optimal. Now, there's a very simple extension to the nearest neighbor algorithm, which is the k-nearest neighbor algorithm. And I'll briefly discuss that, and then we will discuss the role of k. Okay. And the idea is very simple. Now, all the fundamentals, all the basic ideas are in the nearest neighbor algorithm.